Hi guys, hope you're having an awesome day so far. In the last video, we kind of summarized zero, first, and second order reactions. We talked about the differential rate law, the integrated rate law, graphical analysis, units for K, half-life, all kinds of stuff. So now we're going to look at a couple of examples and try to use all this knowledge to try to answer those questions. So we have this reaction here, and we're given some data, and we're asked to determine the order of the reaction, K, and the half-life for experiment 3. So the first thing is the order, and we are given concentration and rate data. So if you remember, to determine the order, you have three options. You can either look at a mechanism, if you are given one, and look at the rate determining step. You can do data analysis, or you can do graphical analysis. So in this case, since we're given some data, we probably would want to do the data analysis where we look at two experiments and look at the change in the concentration versus the change in the rate. So you can pick any of these any two experiments here. I'm going to go ahead and pick 1 and 4 just for a change. And so I'm going to look at the concentration of A in experiment 4 versus the concentration of A in experiment 1. And this one's 1.0 times 10 to the negative second molar. This one's 1.0 times 10 to the negative third molar. So it looks like it's 10 times. I'm going to do the same thing for the rate. So I'm going to look at rate for experiment 4 versus rate for experiment 1. And it is 1.3 times 10 to the negative 6 molar per minute versus 1.3 times 10 to the negative 7th molar per minute. And this is equal to 10. So then you express your change in rate as the change in concentration to some power. And so this is the same thing as 10 to the 1, which means it is first order. So it is first order with respect to my concentration here. Next, I want to find K, and I also want to find the half-life. So let's start with K, and it says we want to use experiment 3. So here we are relating the rate to the concentration, so we're thinking differential rate law. And because we know that it's first order, we're going to say rate is equal to K times the concentration to the first power. So we are going to look at experiment 3. And the rate is 3.9 times 10 to the negative 7th molar per minute is equal to K times the concentration is 3.0 times 10 to the negative 3 molar. And we're going to solve for K. And so K ends up being 1.3 times 10 to the negative 4th. And for our units, this is a first order reaction, so the units are 1 over time units. If you look at your canceling your units as well, this is molar per minute, and this is molar, so the molar goes here, the molar and molar cancel, and you get 1 per minute. And so that's our K. And then finally, we want the half-life for experiment 3. So first order, the half-life equation is half-life is equal to 0.693 over K. So 0.693 over 1.3 times 10 to the negative 4th per minute. And so the half-life ends up being 5,300 minutes. And that's our answer. So in this case, we focused on the differential rate law because we were comparing rates versus concentrations. Okay, let's look at the next example. Example 11, it says, in dilute NaOH at 20 Celsius, hydrogen peroxide decomposition is of the first order. The rate constant is 1.06 times 10 to the negative third, 1 over a minute. If the initial concentration of the peroxide is 0.020 molar, what is the concentration after 100 minutes? So, first thing, they're telling us that it is first order. Now, if they did not tell us that it's first order, so if this did not say that here, you should still be able to tell that it is first order. How would you be able to tell? You can tell from the rate constant, from the units of the rate constant. This is units of 1 over time units, 1 over minutes, and so that tells us that it's first order. So even if they didn't tell you it's first order, just from this you should be able to tell that it's first order. Now, the first thing you want to decide is, do you want to use, sorry about that. So you want to determine whether you use the integrated rate law or the differential rate law. So in the previous problem, we wanted to use the differential rate law because we're comparing or looking at rates and concentrations. Here, it looks like we are looking at a concentration, we are looking at a value of K, and we're looking at time. So if we're relating time and concentration, you want to use integrated rate law. So definitely integrated rate law. And for first order, the integrated rate law, that's the one with the natural log. So let's write the equation down. So natural log of concentration of A at a given time is equal to negative KT plus natural log of the initial concentration of A. This is first order integrated rate law. And again, I knew that I want to use the integrated rate law because I'm talking about time versus concentration here. So what am I trying to find? Well, it says it's giving us the initial concentration, it's giving us K, it's giving us time. They want to know what is the concentration after 100 minutes. So we are solving for this right here. So we're going to say natural log of the concentration of A at 100 minutes is equal to negative, K is 1.06 times 10 to the negative third per minute, times time, which is 100 minutes, plus natural log of 0.020. And we solve for this. So you're going to get that natural log of A at 100 minutes is equal to, if you calculate this side here, that gives you negative 4.06. Do you know how to get rid of natural log? You do E. So you raise E to both of them. So this would be A concentration at 100 minutes is equal to E to the negative 4.06, which ends up being 0.018. And don't forget, you're looking for concentration, so you're looking for units of molarity. Let's look at the next part. It says, how long will it take for 30% to decompose? So let's think about this. Again, here we want to use the integrated rate law. Why? Because we're looking for a time. And so if we're relating time with concentration, you use the integrated rate law. So I'm going to rewrite the integrated rate law here. I'm going to go ahead and use a different color. So natural log of concentration of A at a given time is equal to negative KT plus natural log of the initial concentration. Now, they're asking for how long. So they're looking for T. That's what we're solving for. And we know that K is going to be this number right here. We know the initial concentration is 0.02. And they're telling us that 30% decompose, which means 70% remain. So if we do 0.7 times whatever the initial was, then that's going to give us the concentration at time t. That's one way to do it. So I'm going to do it in two ways, actually, and show you. So 30% decomposed, that means 70% remain. So the concentration of A at time equals T is equal to 0.7 times 0.020 molar. And I think that's 0.014 molar, I believe. So we can plug this in. So natural log of 0.014 is equal to negative, K is 1.06 times 10 to the negative third, 1 over a minute, plus natural log, or sorry, times T. T is what we're solving for, plus natural log of my initial concentration, which is 0.020 molar. And you can solve for T, which is this right here. Now I want to show you a different way to do it. Let's say you are not given the initial concentration, or you want to just make it easier for yourself. You can say, well, if the initial concentration is 100, then after 30% decomposes, my concentration now is 70. So you can plug it in as natural log of 70 is equal to, same thing, the K times T, solve for T, plus natural log of 100, right? If your initial is 100, then what you're left with is 70. A third way to do it is you can say, well, 100% is like 1 in decimal form, so you can plug in 1 here, and what you'd be left with would be 0.7. Whichever way of the three, you will get the same exact answer. So you can plug in the real numbers here, or you can just plug in percentages or 1 and 0.7. Any of those would give you the same value. So if you solve for T in any of those ways, you're going to get 340 minutes. Okay, finally here, this is a summary of what we did in the last video of 0, first, and second order, looking at all of these different things. So I want you to fill this out on your own and then check back. So I want you to pause this video. I want you to fill this table on your own and then replay it again, and it will show you what the correct answers are. But I put it this way, even though you have it in your notes, just so that you have it all condensed in one. That way it might be just a little bit easier for you. So go ahead and pause the video, and then when you fill it up, then check back to make sure that your answers are correct. So welcome back. Hopefully you tried to do this on your own. So you can compare 0, first, and second order, the differential rate law, the integrated rate law, the units for K, the graph, and then the half-life. Remember the half-life equations, you only need to know this one, not the other ones, not 0 or second order.